Good day, good day, good day, and welcome to Africa Teen Geeks. This is a STEM digital school. If you have just joined into this class, this is a grade 12 physical sciences class. I am Nonkulile Matondo, and I am your teacher for physical sciences grade 12. Okay, today is the 9th of July 2020, and I hope that everybody is ready to do some physical sciences. Today we are starting a new chapter, which is the Doppler effect. Okay, we've done we're doing we did a lot of things. We did the work, energy, and power from last week, and we just finished off the chapter yesterday because yesterday we were doing all the revision, but there's still, obviously, you know how I do. There was some homework that I gave you guys for yesterday, just to, you know, put the cherry on top of our revision work. I hope that everybody did it and they were able to do it. So, as per homework, we're going to go through that first before we start on our new chapter. Okay, just reminding you that we are doing the term 3 work at the moment, and we might also start doing some assessments later on next week or sometime soon, but I will let you know. That's going to give you guys an edge on how to start preparing for your final exams, because these are the exams of your lives, guys. Please make sure that whatever it is that you don't understand, even while I'm teaching, you can stop me, send me a chat, and I'll go back and explain wherever you guys are getting stuck. Reminding you that I'm working from the Siavula and the Study and Master textbook, but today I've basically, if you have your Siavula textbook, you'll see that most of the stuff is stuff that I got from there, and we're also going to be working through the textbook as well to explain further with what we're going to be doing today. This is Noguleo Matondo. I am a physical science teacher, reminding you that as well, since you're doing metric, I know that you guys love referencing from different books. You guys can download Snaplify. Snaplify is an application that you guys can get on your phone and on your PC, absolutely free. So if you would like to get some more different textbooks, they're absolutely free on Snaplify. I also use it a lot, and you can also view the textbooks online and offline. So make sure that you get yourself that application while it's still valid. These textbooks are going to be valid up until the 31st of December 2020. This is due to the COVID-19. So they decided to do us some grace and give us free textbooks. So take advantage of the situation. It's not just for physical sciences, but all your other subjects. So if you do get a chance, please be sure to go there and get yourself some Snaplify and some textbooks. Okay, this was our homework. It says on the homework, we're still doing the work, energy, and power. This is the last 3 questions for our revision work that we've been doing for the past 2 days. Okay, it says a van of a mass 2,000 kilogram moving at 10 meters per second on a horizontal surface is brought to rest in a distance of 12.5 meters when the brakes are applied. Okay, so then the question is, calculate the average retarding force. Okay, the retarding force is the frictional force. Okay, and then number B, the van travels up a hill with an incline of 5.74 degrees at a constant speed of 10 meters per second -1. If the van experiences a constant frictional force of 200 Newton, what power must the engine produce? Okay, I hope you still have all your formulas there and you use them for this problem, because we are still doing the work, energy, and power. So this is how we do it. Okay, so we've been given a mass of 2,000 kilogram, and then we have our initial speed, which is 10 meters per second -1. But remember, whenever anything that is brought to rest, the velocity is 0. So the U stands for initial velocity and the V stands for final velocity. Okay, and then our change in distance, because they told us that it stopped at a distance of 12.5 meters. So what are we looking for? We need to find the acceleration in order for us to find the force, because what they're looking for is the force. But for us to find the force, we must find our acceleration, because this car is moving. In this case, guys, we're not going to use the gravitational force, because this is a car that is moving with an acceleration. Okay, so, and another thing that they mentioned is that in opposite, they're looking for the opposing, the retarding means frictional force. Okay, so our velocity, like we said, it's 0 because it comes to a halt. Our initial velocity is 10 meters per second negative 1 squared plus 2a times 12 meters. Okay, and then from there we can make a the subject of the formula and find the answer for acceleration. So you know acceleration has direction. So it says you don't write minus 4 meters per second negative 2. You write 4 meters per second minus 2 opposite to the direction of motion. Okay, are we together? So this is our retarding acceleration. And then from there, now we can move straight to the force that they're looking for. So force is equals to mass times acceleration, which is 2000 times minus 4 meters per second minus 2. And this will give us minus 8,000 newtons. And we can also say it's 8,000 newtons opposite to the direction of motion. Okay, are we together? Guys, if you've just joined in, this is still work, energy, and power revision, the last 3 revision questions that we didn't finish up. So we're just finishing that up. Okay, so number 10 says a motor pumps water from a well 10 meters deep and projects it at a speed of 15 meters per second minus 1. The water pours from the pipe at a rate of 1,200 kilometers per minute minus 1. Find the power of the motor. Okay. Oh, no. Oh, guys, sorry, I forgot the number B of question 9. Sorry about that. So we found the retarding force, right? And then B, they wanted the, okay, they said when now it changes. Now the van travels up a hill with an incline of 5.74 degrees at a constant speed of 10 meters per second. If the van experiences frictional force of 200 Newton, what power must the engine produce? So we know once you have constant speed, your power formula that you're going to use is P is equals to force times velocity. Because why? Because we have a constant speed. So let's check that out. So number B, it says the component of the gravitational force acting down on the incline is given by force 1 is equals to mg sine 5.74. Okay. Yes, so this is our gravitational force. Okay, it's sine. Remember, if we're looking for the force that's parallel to the distance, we would actually use cos, but in this case, the component of gravitational force acting down the incline is given by mg sine 5.74, and this will give us 1960.28 newtons down the incline. Okay, so the frictional force also acts down the incline, and that one is also 200 Newton, which is given to us. So to keep the van at a constant velocity, the force exerted by the engine is given by, the force of the engine is given by F1 plus F frictional. And what is going to be our F frictional? It's going to be 200, and our F1 is what we calculated, which is the mg sine 5.74, and that will give us 2.160.28 up the incline. Okay, so now that you've got the force, we can go straight to calculating the power. And the power in this case is going to be force times velocity. So it's going to be the 2,160.28 times 10 meters per second negative 1. This will give us 21,602.8 watt. Okay? I hope that we are together. So going to number 10. Number 10 says a motor pumps water from a well 10 meters deep and projected at a speed of 15 meters per second negative 1. The water pours from the pipe at a rate of 1,200 kilometers per meter. Find the power of the motor. Okay? So coming here, they said we consider the mass of 1,200 kilometers of water, the work done to raise the water from the well and to project it is given by the equation work is equals to the change in potential energy plus the change in kinetic energy, which is what we have here. And from there, we know that for this one, for the first one, the kinetic energy is going to be 0. And for the second one, there's a potential. Oh yes, this is mgh plus half mv squared, and that will give us 1,200 times 9.8 times 10, and that will be plus this one, which is going to be half times 1,200 times 15, and there we're going to have 252,600 joules. Okay, so therefore the power of the motor is equals to work divided by time, and that will give us 252,600 divided by 60 seconds. Okay, and therefore it's going to be 4,210 watt in 1 meters. Okay, I hope we are all good and we understand what has been done here, and now we can move on. Okay, so it says here today we're going to be doing wave, sound, and light, which is in this case the Doppler effect. We're going to be doing the Doppler effect. So introduction, it says any sound emitted or electromagnetic wave emitted changes pitch in relation to its position. Okay, any sound emitted or electromagnetic wave emitted changes the pitch in relation to its position. So the effect also occurs when moving closer or away from the sound emitted source. The two scenarios are known as Doppler effect. So for example, you're standing here, when I'm screaming at you, or when I'm shouting or making a loud sound like, oh, whoever is standing close to me is going to hear it louder than somebody that's standing further apart from me. Okay, so that's what it means when it says changes pitch in relation to the position. Okay, so if you're standing further away, it's not going to be as loud. The pitch won't be as loud as when you are standing very close to me. So that's why they mentioned that the sound emitted changes pitch in relation to its position. So the effect also occurs when moving closer or away from the sound emitted source. There's two scenarios are known as the Doppler effect. So another fact that we need to know is that the Doppler effect is named after John Christian Andreas Doppler, who was born in 29 November 1803 up until 17 March 1853. Okay, an Australian mathematician and physicist who first explained the phenomena in 1842. And today is 2020, and we are still talking about the phenomena that he created all these centuries ago. Okay? So, the Doppler effect with sound. So, the person hearing the sound is referred to as the observer or the listener. Okay? And the object emitting the sound is referred to as the source. So as mentioned in the introduction, the Doppler effect occurs during the two scenarios. The first one is the source moving relative to a stationary observer. Okay? And number two, the observer moves relative to a stationary source. So it could be either or. Either the person is standing and the source is coming to, the source of the sound is moving towards them or away from them, or the sound is stationary and the person observing is the one moving to and fro. Okay? So those are the two scenarios. So in both scenario 1 and 2, relative motion between the source and observer. Another possibility is a case where both the source and observer are moving. However, that won't be covered into this chapter. So it makes sense, right? That either way, there is some movement, either the source or the observer is moving relative to the sound. Okay? So there's motion that is involved. So the Doppler effect is defined as a change in the observed frequency of a wave when the source or the detector moves relative to the transmitting medium. Okay? So the reason why they say transmitting medium is because the source of the sound is not only a person, could be anything. Could be a music box, it could be a car, could be anything that transmits sound. Okay? So the Doppler effect occurs when a source of wave and or observer moves relative to each other. So it results in the observer measuring a different frequency of the waves in comparison to the frequency the source is emitting. Hence, I mentioned to you guys that if I can scream and say, ah, right now, depending on where you're standing, the pitch is going to be different. In a way, it's going to get lesser, but it is different. It's not the same throughout. It's not uniform. Okay, so it changes according to the position of, or the relative distance between the observer and the source. So the case that will be studied in this chapter are those where the transmitting medium, where there is transmitting medium through which the wave travel is also stationary. Okay, where the transmitting medium through which the wave travels is also stationary. So the first case that we have is a source that's moving and a stationary observer. Okay, so you are the one that's listening to the sound. The sound is the one that's moving. It's either a car, for example, a car playing music. That one is moving, and you're probably standing in a sidewalk somewhere and waiting for the robots to turn green or red, and there's a car that's approaching. That's an example that I can give to you. Okay, so the sound waves can be represented as concentric circles. And what does it mean? It means that where each circle represents a crest or peak as the wave front radiates from the source. Okay, so as a car comes and the music playing, there's all these circles that represent a different waveform or a different peak that the wave is making. Okay, so where each circle represents a crest or peak as the wave front radiates from the source. The representation illustrates the waves traveling away from the source. Okay, so in all direction, and the distance between the consecutive crests or troughs in a wave is constant. Okay, so now we're going to consider the first case. Okay, so this is the first case. In the figure, the crest represented by the black lines and the troughs by the orange line. Okay, so there's a person standing. This is a source, and this is also a source. So what they're trying to explain here is that this is a car, right? So maybe it has a siren. So depending on the position of the car, these two sources will not hear the same sound. Okay, this one, as the car moves away from this observer, as the car moves away from this observer, the pitch becomes low. But as it moves towards the this observer here, it becomes louder and louder and louder and louder. Okay? So I just wanted us to go to the textbook. Here we are. So basically, this is the sound that we're talking about, right? So the sound source in the police car in the middle is in the middle and it's stationary. So for a Doppler effect to take place, the source must be moving relative to the observer. So there's one observer here and there's one observer there. So the car is moving forward, okay? So it means it's approaching the observer. So let's consider the following situation. The source, represented by the black dot, which is right here, emits one wave. The black circle represents a crest or the sound wave. So this is a sound wave that the car is emitting, that moves away from the source at the same rate in all directions. The distance between the crest, represented by the wavelength of the sound, represents the wavelength of the sound. So the closer together the crest, the higher the frequency or pitch of the sound, according to the force is equals to velocity divided by wavelength, where v is the speed of sound, is very constant. So now that we've explained the source and the crest of the source, now we can move on to the second circle. Okay, so as this crest moves away, so it's moving away from one observer, right? As the source is moving away, the source also moves. As the crest moves away, the source also moves and then emits more crest. Okay, so you see now the crests are closer to each other. So now the two circles are not concentric anymore, but on the one side they are closer together and on the other side they are further apart. This is shown on the next diagram. So if the source continues moving the same speed in the same direction, then the distance between the crest on the right of the source is constant. So the distance between the crest on the left is also constant. So these ones are also constant, like these distances are constant, and these ones on the side, they're also constant. So the distance between successive crests on the left is constant, but larger than the distance successive crest on the right. So you see, the space that is made here is because the source is moving away from the side. Okay, so when the car approaches you, the sound waves that reach you have a shorter wavelength and a higher frequency. So which means it's making now the sound is getting louder, the sirens are getting louder because the wavelengths are shorter and the frequency is higher. So you hear a sound with a higher pitch. When the car moves away from you, the sound waves that reached you have a longer wavelength and a longer frequency. So meaning that this person sound that this person hears has a very, very low pitch. Okay? So just as we did before, let us consider okay. Let us consider Let us consider a source, which is a police car in this case, of sound waves with constant frequency and amplitude. Okay? There are two observers, one on the left that will move away from the source, and one on the right that will move towards the source. So we have three diagrams. The first one shows the overall situation with the siren starting at time t1, which is actually the time. Okay? The number two shows the situation at time t2 when the observers are moving, and 3 shows the situation at t3 after the observers have been moved from the for a time interval. So change in time will be equal to t3 minus t2. So the crests and troughs are numbered so that you can see how they move further away, so that we can track which ones an observer has measured. Okay, so there we have it there. So we have the source there. And so now the car is what? Stationary. The people that are moving now are the people in the motorbikes. Okay. So before we had the car was the one that was moving, but now the observers are the ones that are moving. So the observer can hear the sound waves emitted by the police car, so they start to move. So we know the time it takes for them to accelerate. So the frequency of the wave that an observer measured is a number of complete wave cycle per time. So by numbering the crest and trough, you can see which complete wave cycles have been measured by each of the observers at time triangle t. To find frequency, we divide the number of wave cycles by t. Okay. In the time interval that passed, the observer moved towards the police car, and the crest and troughs number 1 through 5, which is what we have here. Number 1, 2, 5. Okay. So the time intervals for each of them is the same. To the observers, this will mean that the frequency they measured is different. So obviously, a motorbike that's here, it's going to hear a lesser sound pitch than the car, than the one that is here. Okay? The closer you get to your source, the higher the pitch becomes. So the motion of the observer will alter the frequency of measured sound from the stationary source. Number 1, the observer moving towards the source measures a higher frequency, like I just mentioned, and the observer moving away from the source measures a lower frequency. It is important to note that we have only looked at the case where the source and the observer are moving directly towards or away from each other, and these are the only cases that we will consider. Okay. So we didn't actually need to analyze both cases. We could have used either explanation because of the relative motion, but at least as long as it makes sense, the concept makes sense to you guys, that it's either the source is stationary and the observers are moving relative to the source, which is to the source and away from the source, or the the the, the observers are the ones that are stationary and the source is moving towards the observer or away from the observer. Okay, so those are the two things that we're going to need. So the formula that provides a relationship between the frequency emitted by the source and the frequency measured by the listener. Remember, there's a frequency when you're listening, you hear a lot of pitch sounds and frequencies. So that is also what the listener observes. Okay, so where FL is a primary perceived by the observer, which is FL. This FL is the frequency perceived by the observer. Then the frequency S is the frequency of the source. V is the speed of the wave. So the speed will the wave will have a certain speed that that is given to you. So the VL is the speed of the listener, and the VS is the speed of the source. Okay. So note that the signs will show either whether or not the relative motion of the source and the observer is towards each other or away from each other. So this table is also important because it tells you if the source moves towards the listener, the VS will be negative. If the source moves away from the listener, VS will be positive. Okay. So when the listener moves towards the source, the VL will be positive. When the listener moves away from the source, the VL will be negative. So you see the difference here. When the source is going to the listener, it's negative. When the listener goes to the source, it's positive. When the source moves away from listener, it's positive. But when the listener moves away from the source, then it's negative. Okay. So basically, this is the big formula that we're going to be using in this frequency. Okay. So let's look at an example. It says the siren of an ambulance emits sound with a frequency of 700 hertz. You are standing on the pavement, okay? So if the ambulance drives past you at a speed of 20 meters per second, -1, what frequency will you hear when number one, the ambulance is approaching you, and number two, the ambulance is driving away from you? Take the speed of sound in the air to be 340. So the first step is you analyze the question. The question explicitly asks what frequency you will hear when the source is moving at a certain speed. This tells you immediately that the question is related to the Doppler effect. The values given in the question are all in SI units, so there's no conversion that is required. So determine how to approach the problem based on what is given. We know that we are looking for the observed frequency with a moving source. The change in frequency can be calculated using this formula. So to correctly apply this, we need to confirm that this is valid and determine what sign we need to use for the various speed. Okay. So you are the listener, are not moving, but we have to consider two different cases. When the ambulance is moving towards you and away from you, we have been told that if the source is moving towards the observer, then we will use subtraction in the denominator, and if it's moving away, addition. So this means that Fs is 700, V is 340. These are all stuff that is given, right? VL is 0 because you, the observer, are not moving. So if you don't move, it becomes a 0. Okay, so the velocity of the source, we have 20 minus 20 meters per second for A. This is when the source is moving towards the listener. Okay, and then for B, it's when it's moving away from the listener, which is a positive 20. Okay, so step 3, now we determine FL when the ambulance is approaching. Okay, so here it's when we're going to use the VS is minus 20. We're going to put it here. The V, we already have it. It's 340, and here it's 0 because remember, our listener is standing still, so there is no velocity. And then we times it by 700, which was also given, and this is what we get. So this, now we need to calculate the FL when the ambulance has passed. And in this case, it's a source moving away from the listener. In this case, it's going to be positive 20, and you're going to substitute everything like it was before, and this is going to give you 661.11 hertz. Okay, so when the ambulance is approaching you, you hear a frequency of 743.75, and when he is going away, you hear a frequency of 661.11. Okay, so that is our example for today. But I'm thinking we'll do some more examples tomorrow and do some problems tomorrow. Let me just see if, okay. So that is all that we have for today, guys. We'll do some more problems tomorrow. We're still doing the Doppler effect. So today I'm glad we just went through we just went through the theory basics of what you need to know, the wavelengths, the crest, the troughs, and the amplitude. So thank you guys so much for joining me in this class. My name is Nonkulego Matondo. I am a physical sciences grade 12 teacher. If you have any queries and questions that you'd like me to explain to you, you can catch me on t33t@gmail.com. Send me email any time of the day. I'll be there to respond to you. And thank you guys so much. This is Africa Teen Geeks STEM Digital School. My name is Nonkulego Matondo, and I'm signing out. Thank you and goodbye.